issue with having issue with Hall and Pam. Okay, so I will start with the Holland pump.
Sir, difference amplifier.
Difference.
Yes, sir.
Okay. Okay, so before starting the difference, I just explain the inverting amplifiers.
Yes, sir.
Okay, so in the last class we covered the non-inverting amplifiers. Okay, what are the non-inverting amplifiers? When we apply our input, like this is my op amp. Okay, if I apply my input on a non-inverting terminal, okay, the condition for that is,
So your screen is not shared.
yeah, I am going to share my screen. Wait a minute. Yeah, that is visible.
Yes, sir.
So in the last class we discussed about the non-inverting amplifier. This is my operation amplifier. Okay, if we apply any input on the non-inverting terminal, so we define two terminals. One is the positive, one is the negative. If I connect my supply voltage, so this is basically called the non-inverting amplifier. The voltage that is applied at this point, we say that this is the VA. Okay, so my output voltage is nothing but this is the RF feedback resistance, input resistance. So my V out is nothing but 1 plus RF by RI times V. Okay, and this RF 1 plus RF by RI is also called the gain of the operation amplifier. We solve in that, we solve also this one. The current that is flowing in this particularly direction is 0, I is 0. So the VA is 2 volts. Okay, if VA is 2 volts and the feedback is negative, so that voltage is also 2 volts. Okay, now the current will be going either in this direction or in this direction through this point, 2 volts. So I apply the KCL, both are the outgoing current, so 2 minus 0 upon Ri plus 2 minus V naught upon Rf. The addition of outgoing current is 0. Okay, so 2 upon Ri plus 2 upon Rf is equal to V naught upon Rf. If I take the LCM, so it is a 2, I'm taking outside, so it is a Ri plus Rf upon Ri times Rf. is equal to V naught by RF. RF and RF cancel out. So it is V naught is equal to 2 times 1 plus RF upon RI. Okay, and 2 is what? VA. So in place of 2, I can write a VA also. Clear? Any doubt? This is the basically non-inverting amplifier we discussed in the last class. Okay. Now, if we
Sir,
connect,
sir,
yeah,
can you tell the KCL application there? 2 minus 0 Ri plus 2 minus V naught RF.
yeah,
Can you come again? Can you
okay.
go through once again?
So basically, thing is that I apply the KCL at this point. Okay. What is the KCL say? Either the incoming current or the outgoing current, the addition of all outgoing current is equal to the addition of all incoming currents.
Yes,
Okay.
sir.
Now what I do, I am just assuming that the direction of current is outside.
Okay, sir.
So that means addition of outgoing current is equal to the incoming current. There is no incoming current. So that's
Okay,
why I put
sir.
as a 0. Okay. Now if the current is outward direction, that is from this 2 volts node, if the current is going outwards, so that means the current direction will be from higher potential to lower potential. So I just
Okay, sir.
2 minus 0 upon Ri. Okay. Now the
Okay, sir.
current is going outward. That means the 2 volts is the higher potential as compared to the V naught. So we are taking 2 minus V naught upon RF, that is equal to 0.
Okay, sir.
Okay.
Okay, sir.
If I say this is the incoming current, like for example, if I say the V naught is higher potential, this is the incoming current. So the equation will be
Sign
this is the
change.
outgoing current, this is the incoming
Minus
current. So outgoing current is equal to incoming current.
incoming current
So 2 minus 0 upon Ri, that
equal
is
to
equal
2
to
minus
V naught minus 2
V naught minus 2.
upon RF. Why? Because the direction of current is incoming. That means this one is the higher potential, V naught is the higher potential, and 2 is the lower potential. So V naught minus 2 upon RF.
Okay, sir.
Okay. So you can write
Okay,
in
sir.
any way. Either you are taking the incoming current, either you are taking the outgoing current. Clear? Any doubt? This is we discussed in the last class. Okay. Now after that, we are going with the inverting amplifiers. Okay. Now what the inverting amplifier says, if in place of non-inverting terminal, I apply my potential on an inverting terminal. The positive terminal is grounded. Okay, we apply the potential here, 2 volts. Okay, this is the RA, RB, RC. Okay, like in that. Now what happened is that if I connected my terminal on a, if I connected my particularly voltage on a negative terminal, this is called the non-inverting amplifier. Again, the condition is that Similar to the in non-inverting amplifier, the inverting amplifier also have a negative feedback. This is the first condition. That means either we are using the inverting or either we are using the non-inverting amplifier. Everywhere my feedback should be a negative. Okay, so you can check. Basically break this one, increase the voltage, apply the incremental voltage, incremental voltage. When it multiply with the negative sign, it will be the downward. Okay, so we are getting the 180 degree phase shift. So first you have to ensure that your feedback will be the positive feedback or the negative. Okay, now
Sir, sir,
yeah.
in non-inverting, it also negative feedback.
Yeah, in positive, either the inverting, either the non-inverting amplifier, always we consider the negative feedback. Positive feedback we will discuss in the week 3 or week 4, where we are going about the threshold level or some particularly the schematic part. That is the part of week 3 and week 4. Week 4 till now we are not discussing the positive feedback.
So, sir,
Okay.
in inverting, it is always be negative feedback.
Inverting or non-inverting, in both case it will be the negative feedback if you use the operation amplifier for some applications. If you are using as a comparator, we use the positive feedback. If we use the calculating for the threshold voltage, we are using the positive feedback. Otherwise everywhere we are using the negative feedback. Yeah, in oscillators also we are using the positive feedback, except this if we are applying or if we are using as a amplifier, as a summer amplifier, as a difference amplifier, as a inverting, as a non-inverting, everywhere we are using the negative feedback.
Okay, sir. Clear.
Okay, if we are talking about the amplifier always use the negative feedback. Remember this.
Okay, sir. Okay, sir.
Any other doubt? uh, if we are talking about, like for example, we are saying that if we are using the positive feedback, our gain, loop gain, basically gain is a upon 1 minus a beta. Okay, and if we are using the negative feedback, gain is a upon 1 plus a beta. Okay, now if I say that a beta is equal to 1, gain is basically the transfer function. You are not saying the gain, we are saying the transfer function, that is equal to v naught upon vi. V naught upon vi. Okay, now let's assume that a beta is 1. So what is the effect of this? A beta is equal to 1. Under positive feedback, v naught upon vi is equal to infinite, because when a beta is 1, denominator is 1 minus a beta, so that means equal to 0. Denominator part is 0, so gain v naught upon vi is equal to infinite, or we can say v naught is equal to vi times infinite. So if I apply the millivolts as input vi, we are getting output voltage as a infinite. So that will be unstable. I think in the signal system we discussed the stability. BIBO, bounded input, bounded output. Remember that? Yes or no? Okay. Remember or not? So I will explain that.
Yes, sir. Remember.
Okay.
For this context, you can explain.
Bounded input, bounded
Yeah,
output
yeah.
for the stability.
For this context, I'm not
In
getting.
this contest, basically, if we provide the input as a millivolt, that means we provide the bounded input, but we are getting the unbounded output because V naught is infinite. Okay, so we can say the system is unstable. Whereas in the case of negative feedback, the V naught upon Vi is equal to infinite when A beta is equal to -1. Okay. Now, if A beta is equal to -1, that means the either A is negative or beta is negative. Okay, if A is negative or beta is negative, we go with the transfer basically system. Mm, we are considering the A is negative, minus A. We already using the negative feedback, that means this is the minus. Now, incremental gain, increase the incremental gain. Here it will be higher, it will be higher, multiply with minus, it will be lower. Downward direction, again it will be multiply with minus A, so it will be high. So either A is negative or beta is negative, and in the negative feedback, automatically it convert into the positive feedback. Okay, so that means A beta is -1 is not possible. Okay, because minus this negative feedback, and because of this minus A or minus B, it will be multiply both, so it become a positive feedback. Okay, so A beta is equal to -1 is not possible. So that means in every scenarios, if we use the negative feedback, that is always stable. Clear? So we use the negative feedback only. Understood?
Yes, sir.
So we are using now, yeah. So that's why we are generally mostly using the negative feedback. Now, if we go to the inverting amplifier, okay, so we see that this particularly is the negative feedback. Now we solve that one. So this is the grounded. So that means this point is ground. So this is a 0 volt. Okay. Now because of the virtual ground concept, this particularly point is also 0 volt. Okay. Now because of this 2 volts, the current that is flowing from 2 volt to the 0, it will be passed here because there is no other path. Okay, the current inside the operation amplifier is 0. We already discussed in the last class. Okay, so the current that is passing from 2 volt to this ground 0 terminal, the current that will be going in this particular direction, it will be passed through this feedback resistance toward the output. So what is the equation at this particular node? So if I say this is the node A, okay, this is the node A. So what is the condition? Apply the KCL. The incoming current I1, This is the outgoing current I2, so I1 is equal to I2. Okay. Now, what is I1? I1 is passing from 2 volt to ground 0. So 2 minus 0 upon RB is equal to 0 minus V out upon RC. So V out is minus RC upon RB times 2 volts. Okay, so if we generalize, we can represent V naught is equal to minus RC. If you see that it is a feedback resistance. So RF, RB, you can see that this is the input resistance. RI times 2 volts is the input voltage V. Okay, so in the non-inverting amplifier, we are getting V out is equal to V in times 1 plus RF by R1. And here we are getting minus RF by RI into V in. Okay, so if your V in is positive, that means your V out is negative. Or we can say that it is a 180-degree phase shift. Or similarly, if V in is negative, V out is positive, 180-degree phase shift. Okay, so that's why we are saying this is as a inverting amplifier. Any doubt? Yes, any doubt?
No, sir.
Okay. Now with this, we are going with the next is the summing amplifier. If we apply or connected two voltage source at a same terminal, so that will be the addition of these two voltages. Two volts, one volt, 2 kilo ohm, 1 kilo ohm, that is grounded, V naught, 1K and 5K. Okay, so again the method is same. Okay, again the method is same. First of all, check the feedback. The feedback is negative feedback. Break the loop, increase the voltage, increase, multiply with minus, it will be downwards. So we are getting a 180-degree phase shift. So feedback is negative. Second thing, if feedback is negative, apply the virtual ground. Okay, apply the virtual ground. So 2 volts and 1 volts both will be here. Okay, the current going inside is 0, I is 0. Okay, so the voltage that will be here, it will be passed here also. So if I say VA and VB, so VA is equal to VB virtual ground. Okay, now you can see the current that is not going inside in this direction. What is the direction of current? This is the direction of current.
Yes, sir.
Okay, so what is the value of current? I. 2 volts and 1 volt both are opposite. That means positive terminal connected with the positive terminal. So that means 2 minus 1 divided by the resistance 3 kilo. So that is the 1 by 3 milliampere is the current. Okay, if 1 by 3 milliampere is the current, so the voltage drop across this point is 1 by 3 volts. Positive, negative. Okay. So the overall voltage across any of the branch, because both branches are parallel, so the overall voltage drop across any of the branch will be same. So what is VA? Either the voltage drop across this branch or the voltage drop across this branch. Okay, so I am basically taking this one. This is my 2 volts. Sorry. This point is VA. That is 1 volt, 1K, 2K, and that is 2 volts. So what is VA? Yes, what is VA? Either the voltage drop across this branch or the voltage drop across this branch, because both branches are parallel, and you know that in the parallel scenario the voltage will be equal. So that means either we consider the voltage at first or we consider the voltage at second. Clear? Any doubt? Student, tell me yes or no.
Yes, sir. No doubt, sir.
No doubts. Okay. Now we have to calculate the voltage in any of the branch. So first of all, we calculate the current. Okay, what is the current value?
1 by 3 milliampere.
We already calculated that it is a 1 by 3 milliamp. Okay, so the value of current I is 1 by 3 milliamp. So this is the positive, this is the negative. The voltage drop across this one is 2 by 3 volts. And the voltage drop, this is the positive, this is the negative. The voltage drop across this one is the 1/3 volt. Okay, why I mention the positive and negative sign in this way? Because the direction of current. Okay, current will be enter in the positive, higher potential, and current will be leaving, that is the lower potential. So the direction of current is 2 volt to 1 volt. So that means the current is entering here and it will be leaving in this direction. So this one is the positive, this is the negative. The current is entering from the top and it will be going to the bottom. So it will be the positive and this one is the negative. Okay, any doubt? Yes, no?
No, sir.
Okay. So what is the voltage at this particularly branch? Positive and positive. Okay, both are the opposite polarities. Same polarity are connected. So that means the voltage at this one is the 2 minus 2/3 volts. That is 4/3 volts. Or you can calculate the voltage from here also. So this is the negative and positive connected. So that means 1 plus 1/3 volt. That is also 4/3 volts. So both branches voltage are same, that is 4/3, and that will appear as a VA. So that means this particularly point voltage is 4/3. If this voltage is 4/3, so VA is 4/3. Okay. If VA is 4/3, that means VB is also 4/3. Now apply the KCL. This is the higher potential, this is the ground, so the current will be flowing outward. Okay, and we are not knowing about V naught, so we are saying the current is also going toward the V naught. Okay, so VB minus 0 divided by 1K is equal to 4/3 minus V naught divided by 5K. Okay, so this is VB is 4/3. So we solve this one. So 4/3 divided by, so 4/3 is equal to 4/15 minus V naught by 5. Sorry, both are the outgoing current, no? So that is plus sign is equal to 0. Plus 4/15 is equal to 0. Okay, so it is a 24/15 is equal to V naught by 5. That means V naught is equal to 24/3 is equal to 8 volts. Clear? Any doubt? Yes, any doubt?
Sir, in the negative inverting input, why did we consider that the current or output?
Wait a minute. Your voice is very low. Just wait a minute. Yeah. Now tell me.
So in the non-inverting input, why we consider that current are outgoing only?
In the non-inverting.
No inverting. Sir.
Okay, in the inverting, we are saying the current is outgoing. Why we are saying the current is outgoing?
Yes.
Okay, so you can say the incoming current also, no problem with that.
So incoming equals to outgoing, right?
Yeah, incoming is equal to outgoing. So the thing is that we know that VB is 4 by 3 and second terminal is the grounded. Okay, so in this direction the current is going outward. Okay, because the current will be flowing from higher potential to the lower potential. 4 by 3 volt is higher than the ground. Okay,
Okay, sir.
now in the feedback we consider any direction, either we consider this direction or either we consider this direction, no problem. Okay, if we consider the current is coming from V0 to, let's say I just say that, sorry, okay, let's say assume the current in this direction. So what is the equation? VB minus 0 divided by 1 is equal to V0 minus VB divided by 5k. Okay, why? Because one is the incoming current, one is the outgoing current, so incoming current is equal to outgoing current. So my equation will be like that. Okay, again if I take, so VB by 1 plus VB by 5 is equal to V0 by 5. The equation is again same. Okay, the answer will be same,
Okay,
but just remember the direction should be clear. If the direction is clear, like for example you are taking that one is the incoming current, one is the outgoing current, and you add them, so it is not possible. Okay, you are saying that current will be from V0 to VB, it is an incoming current, and current from VB to ground, it will be the outgoing current. Now if you add these two and say this is 0, then it will be wrong. Either you consider all the incoming current, either you consider all the outgoing current, either, so the addition of both, either the incoming current or the outgoing current should be 0. This is the first condition. Or if we are taking the other directions, so incoming current addition is equal to the outgoing current addition. You have to follow this rule. Any direction you can take.
okay, sir.
Clear? Any doubt? This is the method one. We can solve with the other method also. I am taking this circuit again. You know the superposition theorem?
Yes, sir.
What the superposition theorem says?
If there is two voltage source or current source, we can put it one voltage source.
Yeah,
We can consider one
we can
and
consider one at
after
a
that,
time.
and
Okay, we
one
can
voltage
consider one
source
source
that
as a
is
time. Yeah.
voltage source is short circuit and current source is open circuit.
Okay, fine. So here we have a two particularly voltage source. Okay, so we can consider the one voltage source at a time. So this is my 2 volts grounded, 2 kilo ohm resistor. This is the 1 kilo ohm that is grounded. Why? Because 1 volt will be the short circuit. This is by op amp plus minus. This is the grounded. This is the V0 5k 1k. Okay, First of all, we calculate the VA. So what is VA? Basically, at this point, the voltage is the VA. Okay, basically at this point, the voltage is VA. And that VA is nothing but the voltage drop across 1K. Okay, so we apply a 2 volt. The current direction will be passing from 2 volt to 2 kilo ohm to 1 kilo ohm. This is the direction of current. No current will be going in this direction because the incoming current for the operation amplifier is 0. No current will be going inside the operation amplifier. So the current in the operation amplifier is 0. So this is the direction of current. So if we consider the 2 volts, what is the voltage at this point? Apply voltage divider.
So 2 into 1 by 3.
4 by
2 into 1 by 3. The
4
voltage
by
of across 1 kilo ohm. 2 into 1 by 1 plus 2. The resistance of the same branch upon the total resistance. That is the formula for voltage divider by C. Okay. So the voltage at this point is nothing but the voltage across the 1 kilo ohm. So what is the voltage? The voltage resistance of the same branch upon overall resistance. So that is 2 by 3. Clear? Any doubt? Yes, tell me any doubt.
No, sir.
Okay. So if VA1 is 2 by 3, what is the V out? We know the formula 1 plus RF by R1 times VA 1. So I consider that V naught 1 is equal to 1 plus RF by R1 times VA1. We know this formula. So we directly use this formula. So 1 plus RF is 5, R1 is 1. So 5 by 1 is 5. So that means this is the 6 volt, 6 multiplied by VA1. VA1 is 2 by 3. So that is the 4 volts. Okay. Now this is because of one voltage source. Now we use the second voltage source. So that is grounded 2 kilo ohm, 1K, 1 volt, or we can make it in another way. 2 volts, sorry, 2K, that is ground. Positive terminal, negative terminal, ground, 1K, V naught. Okay. Now this is VA point. I just say the VA2. What is VA2? The voltage drop across 2 kilo ohm. That is the VA2. Yes, it is a parallel, na? The voltage drop across 2 kilo ohm is the VA2. Now how we calculate the VA2? Again, voltage divider biasing. 1 volt multiplied by the 2K divided by total resistance is 3K, 2K plus 1K. So that is again a 2 by 3. If VA2 is 2 by 3, so that means what is V naught 2? Again 1 plus RF by R1 times VA2. That is 6 times 2 by 3, again a 4 volt. Okay, and according to the superposition theorem, V naught is nothing but V naught 1 plus V naught 2 is equal to 4 plus 4 is equal to 8 volts. So this is the 8 volt. You can see also other method we are also getting the 8 volts here.
Sir, I have one question.
Yeah.
In previous method,
Hmm.
instead of I1 KCL, that
Hmm.
can we use the formula that is V0 equal to 1 plus RF by R1 into
In the
VA?
previous method.
Yeah, this method. We have got VA,
Yeah. So
that is,
if we got the VA 4 by 3,
yeah.
okay, now you can apply the formula.
Yes, you did KCL here.
Yeah, you can apply the formula also.
That will
So
give the same
1
answer.
plus 5 into 4 by 3. So 6 into 4 by 3, that is also the 8 volts.
Yes, sir.
Okay.
Yes, sir. Okay.
So now if I write in the expression form, so V naught is 1 plus RF by R1. Okay. We have to calculate the add these two voltage. Okay, so we are saying V1 into R2 upon R1 plus R2 plus why V1 into R2 upon R1 plus R2? So get a VA1. VA1 is what? If we consider the 2 volts, so 2 volts multiplied by this resistance, so this is the V1 R1, 1 volt is the V2 and 1 kilo ohm is the R2. Okay, so VA1, how we get the VA1? 2 volts, that means the V1 multiplied by the 1 kilo ohm is the R2 upon R1 plus R2. Okay, and how we get the VA2? 1 volt, that is V2 into R1 upon R1 plus R2. Okay, if you have any doubt, you can ask. Into V2 R1 upon R1 plus R2.
Sir, in lecture, that is weighted summing amplifier,
Mhm.
uh, circuit is different. That, and the equation V out is also different.
What is the equation in that one?
V out equal to minus RF
That
by
is
R1
that is
and
that is the in non-inverting amplifier. Inverting amplifier. I am discussing the non-inverting summer.
okay,
Okay, we
okay,
go to the non-inverting summer or inverting summer also.
okay, okay, sir.
Okay, any doubt? This, just remember, this is the summing amplifier for non-inverter. Okay, if we take one more question, you can better understand this one. So 5 volt, 2 kilo ohm, 4 volt, 4 kilo ohm, plus minus 2 kilo ohm or 10 kilo. Okay, you can verify using formula and using superposition theorem. Okay, so if we apply the superposition theorem, so because of 5 volt, we are getting the VA1 here. This is the total VA. So we are getting a VA1 here. So VA1 is 5 volt into 4K divided by total 4 plus 2, 6K. Okay, and if we are considering the 4 volts, so we are getting the VA2. VA2 is 4 multiplied by 2K divided by 6K. Because of this one, we are getting V out. V out is 1 plus 10 by 2. So that is again 6 into 5 into 4 divided by 6K. Okay, K and K cancel out, 6 and 6 cancel out, so it is at 20 volts. Now V out 2 is equal to 4 into 2 into, sorry, yeah, 4 into 2 into 6 divided by 6K. So K and K cancel out, 6 and 6 cancel out, so this is the 8 volts. So V out is V out 1 plus V out 2. So this 20 plus 8 is 28 volts. Okay. You can apply the formula also, you are getting the same answer. Any doubt?
Sir, can you scroll down the page?
Any doubt?
VA1 should be 20 by 6, right?
20 by 6.
6, 6. Denominator 6.
Yeah.
You have written only 20 by.
Okay, you are saying the V out or VA1?
V out.
V out, VA1 is 5 into 4 divided by 6K.
Okay,
Okay.
sir.
So what is V out? VA1 into 1 plus RF by R1.
Okay, sir. Got
Okay.
it.
So RF is 10 and R1 is 2. So 10 by 2 is 5. 5 plus 1 is 6.
Okay, sir. Okay.
Any doubt? Yes, no?
No, sir, no doubt.
Okay. Now the thing is, one more thing, important thing is that your V out is always lies your V out is always lies between the plus VCC and minus VCC. So we are connected a positive supply and negative supply to operate this op amp. This is the VCC and this is the minus. So your V out will be lies in between plus VCC and minus VCC. Okay. In this question, we are not mentioning what is the plus VCC, what is the minus VCC. So we are saying the V out is 28 volts. Clear? If suppose for an example, I mention that plus VCC is 10 volts and minus VCC is minus 10 volts. Then your output voltage V out is only 10 volts. You are getting 28 volt as the output, but you know that your output voltage is lies in between plus and minus VCC. If it is beyond the plus VCC or below the minus VCC, after that particularly VCC point, it will be saturated. Okay, after that VCC point, it will be saturated. So if I draw the curve, so this is the V in, this is the V out. Okay, if you increase the V in, your V out is increases, but after a point, and that point is plus VCC, your output is constant. If you further increase the input voltage, your output is constant. It will not go beyond the VCC point. Similarly, if you apply the negative VCC, it will be apply. You are getting the minus V out, but it will not go beyond a minus VCC. Okay. So your output voltage will be in between plus VCC and minus VCC. We are not mentioning plus VCC and minus VCC, then your output voltage will be the either the 20 volts, 40 volts, 100 volts, 200 volts, any value. But if you mention the value of VCC, it will not go beyond that point. Clear?
Sir, you are not properly audible.
Yeah, now am I audible?
Yes, sir.
Yes.
Okay. So I am saying that if my input VCC voltage is not mentioned in the question, we can calculate V out
any value that is possible. 28 volt, 30 volt, 40 volt, 50 volt, any particularly value of the V out is possible. But if I mention that VCC is plus 10 and minus 10, so the maximum V out that will be coming in this range on. Okay, like for example in this question, if I mention that my VCC is 10 volt and V minus VCC is minus 10 volt, so you are getting the V out is 28 volt. Okay, but your actual V out will be saturated after 10 volts, so your actual V out is not go beyond 10 volts. Okay, why? Because the curve is like that. This is the in x-axis, it is a V in. Okay, y-axis it is a V out. You increase the V in, the V out will be increases. Okay, but after a certain point, if you increase the V in, your V out will be constant, and that constant voltage is VCC. Similarly, in the negative direction, if you decrease the V in, your V out is decreases, but after a certain point, it will be stock constant minus VCC. So if in a question the plus VCC and minus VCC is also mentioned, or it will be shown in the figure, so your output voltage never go beyond that point. You are getting a 40 volts V out, you are getting a 40 volts, okay, but your actual V out is 10 volts. Why? Because after 10 volt it will be saturated. Understood?
Yes, sir.
Okay, so if it is not mentioned in the question, you can take any value of the VCC. So your V out is 40 volt is also possible. Your V out is 100 volt is also possible. But if you mention in the question that this is your plus VCC and this is your minus VCC, so your output voltage never go beyond that point. If it is a higher than VCC, you have to saturate it up to the VCC. If you are getting a 40 volts but your VCC is 10 volts, so your actual output is what? 10 volts, not a 40 volts. So 40 volt you are getting as a output, but it is wrong. Your exact output is 10 volts. Remember this thing. Any doubt? Okay, if we have a summing at a inverting op amp, so this is the ground connected a R1. We have two voltage source, one V1. This is RX, R1, V2, R2, and R. Okay, so we know that this point voltage is 0, so that means this point voltage is also 0. Okay, now you can solve using the superposition theorem. So first we consider V2 as a grounded. Okay, so I'll just copy paste this one. Okay, now V2 is grounded. Now see that if V2 is grounded, so this point is grounded, that means this point is grounded. So this is the 0 volt, this is the 0 volt. Okay, so if resistance both terminal connected with the 0 volt potential, so there is no use of this resistance. So either we connect it or we remove it, there is no effect. Okay, if we connect both terminal of the resistance through the ground terminal, okay, so there is no particularly flow of the current, there is no particularly voltage drop across this resistance. Why? Because both particularly terminal of the resistance have a same potential. Okay, have a same potential. So if potential is same across both terminals, so there is no current flow, there is no voltage drop. So either we consider that resistance or we are not considering that resistance, there is no effect of that resistance. Okay, so what is the formula? If I connect a V1, so the formula with respect to V1 is minus RF by R1 times V1. Understood? Now we apply the second superposition theorem. So in this case, what we do, I am taking this circuit and this one. Okay, again, this point and this point has a zero potential, so zero potential, zero potential. That means there is no use of this R1. What is V out? I just say the V out 2 and V out 1. So V out 2 is minus RF by R2 times V2. So the overall voltage is what? Minus RF I am taking common, so it is a V1 by R1 plus V2 by R2. So that is the voltage, summing amplifier with a weighted sum of the voltage. Okay, if we have a N resistance, so that is equal to minus RF summation I is equal to 1 to N VI upon RI. Okay, if we have a N resistance, so V1 plus upon R1 plus V2 upon R2 plus V3 upon R3 plus Vn upon Rn. Okay, if we have a N resistance. Clear? So this is for inverting op amp. Yes, any doubt? Clear, any doubt? Hmm.
No, sir.
Now
Yes,
we
sir.
go to the yes, no doubt.
sir.
Now we go with the difference amplifier. Okay, in this difference amplifier, we connect one voltage source at a R1 point, positive terminal, and one voltage source at a negative terminal. Okay. Now again, two method, either you can solve using the superposition theorem or you can solve directly also. Okay, so if we solve directly, so again the feedback is negative. Okay, so this point voltage is VA, this one is VB. So if no current will be flowing inside the operation amplifier, that means the current in this direction is zero. Okay, if current is zero, so that means the voltage drop across this point V is also zero. So we can say VA is equal to VB is equal to V1.
Sir, your voice is not audible. You are not audible, sir.
Hello. Student, am I audible now?
Yes, sir.
Yes, sir. Now you are audible.
Okay. So, okay, so I just explain it again. So we apply the VA is equal to VB is equal to V1. That point is clear.
Yes, sir.
Okay. Now at VB point we apply the KCL.
Okay, so the current we consider that the current coming from V0 to VB in the incoming current for VB point. Okay, and the current from VB to V2 is the outgoing current. So we apply the KCL at VB point. So the incoming current is V0 minus VB by RF, that is equal to outgoing current. What is outgoing current? VB minus V2 by R2. Okay.
Yes, sir.
Now if we solve that, so we know that VB is what? V1. So V0 by RF is equal to, if I take VB here, so this is the V1 1 upon RF plus 1 upon R2 minus V2 by R2. So V0 by RF is equal to V1 into R1 plus RF divided by R1 RF minus V2 by R2. So V0 is V1. This RF and RF cancel out. R1 if I divide, so this is the 1 plus RF by R1 minus V2 into RF by R2. Sorry, RF R2. This is R2.
Yes, sir.
This
Sorry.
is R2. This is R2. Okay. So this is the because of non-inverting amplifier, and this is because of inverting amplifier. Okay, and there is a difference, so that's why it is called the difference amplifier. Okay. Now if I say that I have two voltage source,
Sir, you are not audible.
no, I am not telling, I am not speaking anything. I just draw the circuit. Okay, so this is my circuit. Now, if I say the output voltage, so output voltage is what? The addition of V1 voltage, sorry, addition of output voltage with respect to V1 plus addition of output voltage with respect to V2 minus addition subtraction of, sorry, minus V out because of V3. Okay, so here we use the summing amplifier equation. Okay, so we already discussed what is the summing amplifier when we connect a two voltage source at a positive terminal. So this is my equation. Okay, so I am using this equation. So control C. I am using this equation. Okay. So this is the output voltage because of V1. This is the output voltage V out because of V2 minus the voltage because of V3. So V3 have a voltage is minus of RF by R3 times V3. So that is the V out because of V3. Okay, you can try to solve this question also. You are getting the same formula. You can try to solve this question. Apply superposition theorem. Yes. Are you trying that? Yes. Are you trying that? Hello.
Yes, sir.
Just solve it. Solved it or not? Isn't any doubt in that one? Any doubt?
Sir, can't solve that.
Can't able to solve, or can you are trying that one, or basically any issue in that?
Can you give us some values?
Okay, give some values. So V1 I consider that is a 2 volts. V2 I consider again a 2 volts. V3 I consider as a 3 volts. R1, R2, R3 is 1K, 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 and that is 5K. Okay, so the feedback is negative feedback. So first of all, this voltage we have to find out. This is VA. This voltage is VB. Okay. Negative, because of negative feedback, we can say VA is equal to VB. Okay. Now we apply the VA. VA calculate the first of all VA. So what is the method to calculate the VA? Either we use the superposition theorem, or I can directly solve that. So if we apply the superposition theorem, so first we consider that this particularly voltage, consider this voltage. Okay, so if I consider this voltage, this is short circuit, this one is short circuit. So 2 volts will be drop across 1K and 1K. So what is the voltage drop across 1K? 2 into 1 divided by 2, 1K divided by 2K. Okay, so the 1 volt will be dropped. Now consider this as a short and this as a voltage source. Okay, so again this 2 volts will be flowing from 1K and 1K to ground. So what is the voltage drop across this another 1K? R2.
Is same value.
Yeah,
That will be also same value.
yeah, same value. So that is 2 into 1 divided by 2 is 1 volt. So now VA is 2 volts. Addition of these two voltages is the 2 volts. So VB is also 2 volts. Okay. Now I assume the current is from V naught is it is entering current, and the current from VB it is the outgoing current. So V naught minus 2 volts, because VB is 2 volt, upon 5K is equal to 2 minus this V3, that is a 3 volts, upon 1K. Okay, so V naught minus 2 is equal to minus 5. So V naught is equal to minus 3 volts. Okay, you can use. Wait a minute. You can use formula also. So we know this is the formula. So this is my complete formula. Okay, so V naught is 1 plus RF. RF is 5 divided by this R3. R3 is 1 into V1 is 2 volts into 1 divided by 2 plus 2 volts into 1 divided by 2 minus RF is 5 divided by 1 into V3. V3 is again 3 volts. Okay, so this is 6 into 1 plus 1, 2 minus 5 into 3 is 15. So 12 minus 15, that is again a minus 3 volts. Okay, so you can use any method. Superposition theorem, you can apply the direct method also. How we calculate the direct, using the direct method to calculate the VA voltage. Okay, so this 2 volts, the current is flowing in this direction. Okay, so what is the current I? I is 2 minus 2 divided by 1 plus 1. Okay, the voltage positive and positive. Okay, voltage positive and positive, so they will be subtract divided by the total resistance. Resistance is 1 kilo ohm plus 1 kilo ohm, so that is the 0 milliampere. Okay, so the current is 0 milliampere. That means the voltage drop across R1 is 0. The voltage drop across R2 is 0. So what is VA? VA either this branch voltage, that is 2 volt, or the second branch voltage, that is also 2 volts. So VA is directly 2 volts. Okay, if VA is directly 2 volts, then we calculate the output voltage. So what is the output voltage? V out VA into 1 plus RF by R1 minus V3 RF by R3 minus V3 RF by R3. So VA is 2 into 1 plus 5, 6 minus 3 into 5, that is minus 3 volt. Okay, so these are the different method you can solve it. Now we go to the one important topic, that is the Holland pump. What is the Holland pump? Says that if we have an operation amplifier, first of all, the Holland, what is the Holland pump? The Holland pump is basically a transconductance amplifier The concept is given by one scientist, Holland, so that's why it is called the Holland pump. So according to the Holland pump, what we are saying is we apply the input voltage V in, okay, and with respect to V in, we are getting the output voltage V I, output current I out. Okay, we apply the input voltage V in, and with respect to V in, we are getting the output current I out, and that output current I out is independent of output voltage V out. Okay, we know the relation that V in, basically V out is the function of V in. We know this thing. Okay, if we apply the positive terminal voltage or inverting, we are getting minus Rf by R1 times V in. If we are getting a non-inverting terminal voltage, so I am getting output voltage is 1 plus Rf by R1 times V in. So that means output voltage is always a function of input voltage. Okay, but now the scenario is that output voltage is function of V in, but the Holland pump is a pump source that will be providing me the current, output current I out, in a way that this out is not a dependent on V naught. That is dependent on I V in, but that is not dependent on V out. Okay, so this is about a Holland pump. Okay, so first of all, if we are saying that we required a I out, so that means we required a current source. Okay, so what should I do? I just take a voltage. How we create a current source? We create a one voltage, that is the reference voltage, and we apply a one resistance R. So we are getting some current I is equal to V ref by R. Okay, so we are getting one current source. So I just replace that one is the V ref by R. This is the R, and we are connecting a Z. Okay, so we are saying that this is my current source. This is my current source. Now the point is that we know that every current source has a internal resistance in a parallel. So that particularly R shows the internal resistance of current source. Ideally, the current R should be infinity. Yes, ideal current source
Yes, sir.
infinity.
Yes,
An
sir.
ideal voltage source
It should be zero.
always zero. Yeah, good. So basically, if R is infinity, that means no current will be going in this branch, and all current will be passing ZL. Okay, similar to the voltage source, we have internal connected in series. Voltage drop is zero. But
Sir, your
yeah,
voice is breaking.
my voice is breaking again. Okay, now it's fine.
Yes, sir.
Okay.
Please tell again.
Hmm. So the current source, we are saying that one resistance, internal resistance that is connected in a parallel. And for the ideal scenario, we assume that the resistance is infinite. but practically the infinite resistance is not possible. Practically the infinite resistance is not possible. So if we have a some resistance R, that is the maximum resistance we can assume in terms of mega ohm. So that means there is also a current flow I. Okay, there is also a current flow I. And what is that current flow? If cross this one, so that is VL by R. Okay.
Sir, small current will flow, no?
Yeah, small current will flow.
Yes, sir.
R is maximum, so small current will flow.
Yes, sir.
Okay. And what is VL? That is the current V ref upon R into ZL. So this is VL. So what is the current in this branch is? I is VL by R. So that is the V ref upon R square into ZL. Okay. Any doubt? Yes, any doubt? So we are getting a less voltage VL as compared to required because some volt current will be flowing in this one and remaining current will be passing through the ZL. To avoid this effect, what should I do? I just Vref by R. This is the R ZL. So we add some particularly current connected some current source from here. That is the VL by R. Okay. So the current V reference by R and VL by R. So what is the total current here? V ref by R plus VL by R. Incoming current. Okay. Now out of this incoming current, the VL by current will be R current will be passing here. So minus VL by R. Okay. So the remaining current will be passed here. So the remaining current is V ref by R. Clear? Any doubt? So we add the VL by R current source. So this particularly the current that is passing in VL by is this resistance. It will be compensated by this current. Okay, the current that is passing in this R resistance, it will be compensated by this extra current source, and the overall current will be passing in ZL. Clear? Any doubt? Yes, any doubt? Say yes or no.
Sir, then it is independent of output voltage. How? Uh,
Independent on output voltage. Yeah, I will tell you. Okay, so we will go with that part also. Okay, so this is the V ref by R. ZL. This is the VL by R. We are using one more resistance and we are connected the VL to VL with the R resistance and with the R resistance. So the direction current will be the VL by R. So we required a 2 VL voltage. We are getting VL here. So how we convert VL into 2 VL? With one operation amplifier that we are using in a positive feedback. Okay. In the negative, we are connecting one resistance R. In the feedback, we are connecting one resistance R. Okay. So we are getting a 2 VL voltage here. Now this 2 VL will be connected at this point. Okay. This R and this R both are same. So we remove this R and directly connect it to this point. So we are this is my point 2 VL. We are connecting this as a R. Mm, This is my R. This is R 2 VL. This is ZL. So we are doing okay. Now for the simplification, we are doing this is my VREF by R. This is by VL by R current. Okay. So in place of adding this VL by R current here, should I add a VL by R current in this branch also? Okay. In place of adding VL by R current at this point, what should we do? We are adding the VL by R current at this point also. Okay. So you are getting a V reference by R here. If we are not connecting here, so the current VL by R is passing here. Here the current is V ref minus VL by R. Okay. Now we add VL by R at this point. So again the current in this ZL is V ref by R. Okay, so we are in place of this point, we are adding the VL by R current at this point. So this is my ZL. to add VL by R current. So this is the R resistance. This is my op-amp. The VL point is coming here. So the VL point is connected on the positive terminal. This is 2 VL point. This is the negative terminal. We required one resistance R. One is feedback resistance R. So this is the R, this is the R, and this one is connected with a ground. Okay. So VL by R is here. So the current that is passing is Vref minus VL by R. Okay. From here we are getting the VL by R current. So the here in this branch the current is Vref by R. Understood the concept? So what should we do? In place of this one, I connect a VL by R at this point. Any doubt? Yes, any doubt? Till now, any doubt? So we are getting V reference by R. This is R. Now this is the VL point. I connect this VL point in the operation amplifier, ground, resistance, resistance R and R. So we are getting 2 VL. Now this 2 VL will be passing through R. Connecting a ZL. Okay, so we basically do redraw this circle in this way. Any doubt? Just any doubt? Okay. So if now this particularly complete things will be only to get a voltage, sorry, current Vref by R.
Sir,
Yes.
op-amp, there is resistance
Which resistance? This
with
one?
yes, yes.
R. Same resistance. R, R, R. We only change this, we only basically use this point here, shifted here to here. Okay.
Yes, sir.
This particularly current will be adding in this point. So we keep this point as it is. We keep this point as it is. We only connect one path and ZL connected here. I just this ZL I just remove it from here and I just shifted a long path and ZL here. Okay,
Yes, sir.
I can do that one because this is the ZL connected this point.
Yes,
Only
yes.
I am using this wire long.
Yes,
Okay,
yes.
this wire I just take as a long. So I just use this one. Okay. Now all this particularly process will be doing only to get the Vref by R, current and the load. Is it clear? Why we connect this operation amplifier? Because we are if we use the current source in the parallel of the current source, there is some resistance, internal resistance, the value is high, but there is some internal resistance, and because of that one, my output voltage will be changed. VL will be changed. Okay. To overcome the effect of this resistance, and to eliminate the effect of this voltage draw current passing through this resistance, we use this operation amplifier. Okay, and finally in ZL what we are getting? Vref by R. Clear?
That is current, input current, that is.
Yeah, so that is, so across the ZL what we are getting? Vref by R.
Yes, sir.
Okay, now we replace again Vref by R as a voltage source with the resistance in series. So this is the Vref, this is the R, and we use this complete circuit, and in the output we are connected with ZL. So the current in ZL load resistance is nothing but Vref by R. So the current in ZL, that is not dependent on V out. That is only dependent on the Vref. And Vref is nothing but V in, input voltage. Okay. The current in ZL is not dependent on VL. The current in ZL is only dependent on Vref. Is it clear?
Yes,
The
sir.
current in ZL is not dependent on VL. It is dependent on Vref or V input voltage. We say the input voltage V in or Vref. It is not dependent on VL. So that particularly structure is called the Holland pump.
So, sir, we want full input current will pass through the load, that is ZL.
Yeah,
No
through
disturbance.
complete current will be passed through the
Yeah.
load.
No
ZL.
disturbance due to
Yeah, there
voltage.
is no particularly, if you change the value of basically voltage, so your output will be current will be changed.
Yes, sir.
Okay, if you change in the internal circuit, if you change the ZL, if you change the ZL, your VL will be changed. Your VL is changed. Okay, if you change the ZL, increase or decrease, your VL will be maybe increase and decrease, but your IL is constant.
Yes, sir.
Okay, because IL is dependent on Vref by R, that is not dependent on ZL. If IL is also vary, If IL is also vary, so we can say the IL is a function of VL.
Yes, yes.
Okay, but now the IL is constant. That is Holland pump. Okay, so this Holland pump basically create a negative resistance also, negative resistance effect also. So we will discuss that one in the next class. Okay, any doubt? Any doubt?
No, sir.
Okay. So I think we stop here.